Hello everyone, welcome to Vihari Academy. This is Dr. Rekha Piliadula, researcher by profession. Today we are going to discuss about the different types of integrals that are very much needed in order to understand many concepts in electrodynamics. Basically, we have three types of integrals: line integral, surface integral, and volume integrals. So now, without going into much deeper details about these integrals, let us just have an overlook which is suffice to understand the concepts in electrodynamics. One thing we have to understand is that the line integrals are useful when we are considering one-dimensional system like line, which we usually call it as path. And surface integrals they encounter when we consider a surface or a two-dimensional system. And when it comes for the volume integrals, it deals with a region, a three-dimensional space. So I'm just taking a cube as an example, which can generate so this is a small infinitesimal region that can cover a three-dimensional space. So here comes the concept of volume. So if we are evaluating a strength of a field or any function which is enclosed by a volume, the volume integrals are very much useful. So now let us just consider what are the boundary points for these three different dimensions. If we are considering one dimension, the boundaries will be the points, initial and end point. Say for example, A and B. When we consider surfaces, the boundaries will be the path or lines are enclosed. Lines are the boundaries of this surface. When we consider volume, the boundaries will be the surfaces. Like this is one surface, this is another surface, this is one more surface. Similarly, front and back also another two surfaces will cover up that volume or a region in the three-dimensional space. So what is line integral? When we know the value of a function within an infinitesimally small region, then we can integrate that value in order to know the function for the whole system. That is the main purpose of integrals. And here, as we are taking line integral, the boundaries will be the two endpoints. I mean the initial point and the end point. This will be the boundary point. So we are going to integrate the function from point A to point B. And say for example, we have a vectoral field represented by V bar, and so we are going to evaluate this vector field through an infinitesimal displacement. And what about surface integrals? As surfaces are two-dimensional, we have to integrate them with respect to an infinitesimal patch of surface. That means we are considering this surface, and this surface is bounded by the path or the lines, and which is having a particular surface area, and that surface area can be denoted as dA bar, which is a vector whose direction will be perpendicular to that surface. That means if we have a surface which is enclosed in YZ plane, the surface area direction will be x-axis, along the x-axis. So this is the surface integral, and we are considering the same vectoral field V bar. We are going to integrate it with respect to this surface area. When it comes to the volume integrals, as it is three-dimensional, we have to considering integrating that function along three different axes. So usually volume integrals are mostly applied onto the scalar fields, and the volume is a scalar. Again, we represent volume integral like this, three integrals along each direction. I mean three integrals for dx, dy and dz. So the boundaries for these integrals will be surfaces. Say for example, we have V bar and d tau. Let us say V bar is having the components as Vx along I cap, Vy along j cap and Vz along k cap. Here d tau is the, in Cartesian coordinate system, d tau is the volume, and it can be represented as, d tau is the infinitesimal volume element. It can be written as dx, dy and dz. So here we are going to integrate this vectoral function or vectoral field V bar with respect to the volume element, infinitesimal volume element d tau. So this comes like this: Vx I cap plus Vy j cap plus Vz k cap with respect to the volume element dx, dy and dz. Remember that each element of this, each component of this vector should be integrated with respect to x, y and z. In our last session, we understood different types of derivatives that we can apply for any scalar or vector. They are gradient of a scalar, divergence of vector and curl of a vector. So today we have seen what are the different types of integrals. Line integral, volume integral and surface integral. Line integral is something from point 1 to point B and through an infinitesimal displacement. Surface integral is across a surface with respect to the surface element, surface area. Volume integral is integration of a function with respect to the volume element. For line, the boundary points will be, boundary will be the 2 points to endpoints. And for volume, the boundary will be the surface that is enclosing that volume. And for surface, the boundaries will be lines. So now let us see how we can combine these two concepts, like the derivatives and applying integrations for them, and how we can make different types of theorems. We have different theorems with respect to the combination of derivatives of a function and by applying the integrations for them. The initial one is theorem of calculus, which is the basic one, which explains the real meaning of an integration. If we have a path that is starting from point A to point B, and to know the value of the function through an infinitesimally small displacement vector di bar, derivative of f can be, this is a function, derivative of f can be written as df by dx into dx. Here dx is the infinitesimally small displacement. So if we have this value, the derivative of a function through a small infinitesimal distance, then we can integrate it to know the total value of the function from point A to point B. So let us say that derivative of f with respect to x is f prime, that means first order derivative. Then by integrating it both sides, so it says that if we integrate this small value, a small variation of a function with respect to x, then the value of the integration from point A to point B will be the value of that function at the boundary points. That means f of b minus f of a. And coming to the second one, that is theorem of gradients. Say for example, we have gradient of a scalar function s, then if we integrate it from a point A to B with respect to the infinitesimal displacement, then the value will be the difference between the value of the function at two endpoints. Then coming to the theorem of divergence, if we have a vector field denoted by v bar and this is the divergence of the vector field, the volume integral of this divergence with respect to a small infinitesimal volume element, then the value is equal to the value of the function across a infinitesimal surface area enclosing that volume. That means surface is the boundary of this volume element. And coming to the theorem of curls, curl of a vector within an enclosed surface area is equal to the value of that function integrated along the path that is enclosing that surface. That means the boundary line, along the boundary line. Here, this is called Stokes' law. The theorem of divergence and theorem of curls, these two are having a lot of importance in electrodynamics. So the theorem for curls is called Stokes' law, and the theorem for divergence is called, it has two names, Green's theorem or Gauss theorem. So this is all about the integrals and the different types of theorems which are having a vital role in dealing with electrodynamics. So in the next session, we will look into the different types of coordinate systems. This is very, very important because when we encounter different problems while dealing with electrodynamics, we need to know different types of coordinate systems and how we can change one type of coordinate into another type of coordinate. So this is very important, so we can frame them up together in a single session. So we'll discuss about it in the next session. Thank you.